Well, let's consider an example. Uh, let's consider an example. Let's consider x to be, let's take x to be Rn. Let's take the a finite dimensional a finite dimensional module over the Clifford algebra. Let's take x to be Rn with the standard metric. So in this case, G will be the sum for I from 1 to n, AI d over dxi. Well, we take E equal Rn cross V. So the operator will act on functions from Rn to V. Now, what does this operator do? Well, it takes a function, differentiates it with respect to xi, and the result is again a function from Rn to V. And then we multiply it, Clifford multiply it by AI, where correspond to an orthogonal basis of Rn. In particular, AI, the commutator of AIHA is minus delta ij minus delta ij times the identity matrix, which follows from the same identity in the Clifford algebra. Let's not check. It's not very hard to check. Let's not check it. Okay, now Though this operator is has the property that d squared is
Сейчас, подождите, аита это кто? Как
well,
объект?
I is the identity of V.
No, A.
Well, AI is the image of the ith orthogonal basis vector of Rn under the action of the Clifford algebra on V. То есть у нас есть алгебра Клиффорда, она действует на каком-то там вещественном, то есть там вещественном или комплексном, в общем, для определенности давайте вещественном, а сейчас все вещественное. Значит, она действует на вещественном пространстве в каком-то. Значит, мы выбираем ортогональный базис в значит, каждому элементу в базисе соответствует какой-то эндоморфизм В. Ну вот, значит, мы его обозначаем аита. Вот. Дальше, значит, из отношения в алгебре Клиффорда следует, что, значит, что значит, если у нас есть ортогональные векторы, то well, I forgot the 2 here. It's minus 2. Minus 2 delta j. So if we have orthogonal vectors in Rn, then it follows from the relations of the Clifford algebra that oh, sorry, no, sorry, this is wrong. It's not commutator. It's supposed to be the anti commutator. So let me write this explicitly. Blah blah blah. AI AJ plus AJ AI. Yeah, that's better. Because otherwise it would be quite wrong. But every element commutes with itself. It's not minus the delta. Окей, Егор, значит, понятно, что происходит?
Ну, то есть оператор это просто вот то, что написано, да, из C бесконечный, просто какой-то элемент C бесконечности.
Значит, это оператор, который действует на функциях из Rn в V.
Он действует на таких функциях.
Да, ну, V не обязательно одномерно, может быть, какой-то, значит, оператор какой-то действует.
Ну, а ит это просто матрица, короче.
Да, ит это просто матрица. То есть мы функцию сначала дифференцируем, получаем функцию. Значит, потом, значит, функцию мы умножаем на матрицу, но это мы вроде умеем, потому что, значит, эта матрица получается здесь, в общем, там здесь алгебра Клиффорда.
Ну, вот теперь понятно.
Okay, now what is d squared? Well, it follows from this relation and from the fact that partial derivatives commute. and all matrices AI are constant, they do not depend on X. Well, I think yes, and we need to multiply it by -2 again. Where or do we? We'll see. Where delta is the square root. Delta is the sum of d squared xi squared. Blah, blah, blah. Yes, I think so. Anyway, we get something which up to a scalar multiple is the Laplacian is a square root of the Laplacian operator, which reviews an operator on which acts on functions from Rn to V. Okay, does everyone agree? I may have forgotten a square root, or a plus, or a minus, or something else.
Ну, в общем, да, просто скобки раскрыть.
Да, просто разрешить скобки, совершенно верно. Ну, еще воспользуюсь тем, что значит, аиты постоянные, поэтому там как их не дифференцирую, значит, получим 0. Okay. Now, well, there are some more particular cases, but for example, we could take n equal 2 and get the Cauchy-Riemann operator, or we could take n equal 1 and get some other operator. By the way, I don't know which n was is more relevant to physics than the other ends. Probably 2 or 3 or 4 or 5. Well, I would guess it's probably 4. But it's a random guess. Anyway, let's so unless there are explicit requests from other participants, I suggest we move on to other examples. Well, the next example. No, hold on. Work. Okay. So another example will will also be familiar to us. X arbitrary we return to our assumptions. The tax should be compact, without boundary and oriented. Now we take S equal the Clifford algebra itself. So well, in this case, my claim is that well, first of all, this Clifford algebra is isomorphic to the cotangent bundle of X, and my claim is that in this case D is simply the Hodge no the Durham operator symmetrized, meaning D plus the adjoint of D. So, in particular, the Dirac operator generalizes the Durham operator. Now, let's see. Let's see how the Dirac operator generalizes the signature operator. Well, the Dirac operator is self-adjoint. If the Clifford action is flat. Sorry, parallel. By the way, well, this is something I've already said a few times, but does it make any sense? Леонид, значит, понятно ли, что означает слова, что действие Клиффорда параллельно, или какой-то бред?
Ну так.
Ну, скорее бред, ничего не означает. Хорошо, давайте вот. Okay, so let's explain what this means. Okay, so we have a connection. On S, and suppose we also have one on Tx such that the metric is parallel. Now we've we've come to the same question again. What does it mean? What does it mean that the metric is parallel? Well, here we talk about the Clifford action, and we say it's parallel, and we want to define what this means, and then we need to define what it means for a metric to be parallel. Well, to explain this, let's consider a more general let's consider a more general yes, so let's consider a more general situation. So suppose we have E1, E2, X smooth factor bond. So if we have connections on on both, yeah, that's one too many. If we have connections on both E1 and E2, we also have a connection on E1 tensor E2 and a connection on the home bundle from E1 to E2. Well, it's pretty straightforward what these are if we use the second definition of a connection. Suppose we have a family of linear isomorphisms between the fibers, then we can take the tensor product. We get a family of isomorphisms of the fibers of the tensor product, and it works similarly for the homes. And this is straightforward from the second definition of a connection. Now, for the record, let's note the following formula, which in which the tensor product is meant to contain the cotangent component at the right place. Basically, this well, the formula gives one a section of E1 tensor Tx T upper star x tensor E2, and then we just transpose T upper star x and E2. Okay, so we may need this formula later, but at the moment it's well, it's just for information. Okay, now we understand what it means for an element of for a section of the tensor product to the parallel. If we have connections on each bundle individually, and well, similarly, we starting from the connection on each bundle, we get a connection on the home bundle, and so on. So a metric, and we also get a connection on the dual bundle, and the metric is a section of what? Well, it's a section of the second symmetric power of T dual of X dual. Okay. Okay. Once we have connections on T upper star of X, we also have a connection on this on the second symmetric power. Well, it basically follows from this construction, and then we just note that this connection preserves the second symmetric power, and in fact the third symmetric power, and all the rest. And so we get a connection on the second symmetric power, and it makes sense. It makes sense for us to require it to be parallel. We'll recognize what this means, and so this definition makes sense. Так, значит, Егор, Володя, Леонид, значит, имеет ли происходящее хоть какой-нибудь смысл? Simon, does any of this make any sense, sort of, or not at all?
Yes. It's clear.
Right, так, значит, Леонид, понятно ли происходящее, или непонятно совсем, или что-то посередине?
Все понятно.
Так, хорошо. Значит, Егор, Значит, вот то, что мы только что значит, определили, это не более не менее, чем связанность индуцированной, то есть связанность, значит, метрическая связанность, то есть связанность, которая согласована с метрикой.
Ну да, это понятно. Всё, в общем.
Так, значит, Володя, имеет ли происходящее хоть какой-нибудь смысл?
Ну да, вроде бы да. Ну, то есть я тут, честно говоря, там концовку не уловил. Вот.
Значит, но если у нас есть связанность на каком-то расслоении, то у нас есть связанность на там, тензорной степени этого расслоения, там, на внешней степени, на симметрической степени, в общем, на всевозможных таких вот значит, конструкциях.
Мгм.
Ну, как она определяется? Ну, если мы ее определяем как семейство изоморфизмов слоев, то значит, мы просто берем вот то семейство, которое у нас было, и применяем к нему соответствующие функции. Там, внешняя степень, тензорная степень, там еще какая-нибудь степень. И получаем значит, изоморфизм там.
Ага.
Поэтому мы можем требовать от метрики как сечения там такой-то там, тензорной степени или там симметрической степени, чтобы она была параллельна. Ну вот требуем. Вот что получается. Okay, so now we have a connection on. Now we understand what this expression means. Now we come back. The Clifford action. Well, the Clifford action. What is it? It's a map from. It's a map from CL T up to star of X tensor S to S. Well, we have connections everywhere. We have a connection on CL T up star of X. We have a connection on S. So we have a connection on the home bundle, and we require that the action is we require that this connection preserves the Clifford action, or in other words, the Clifford action should be parallel. Okay. Well, now where do we get a connection on the Clifford algebra from? Well, we have a connection on T up to star of X, and then we pass to the principal bundle, and then back to the induced bundle. Okay. Now. Okay. Now. Blah 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 blah. If the Clifford action is parallel. So now we understand what this means. Maybe we understand what it means for the Clifford action to be parallel. Okay. Well, the main problem with self-adjoint operators is that they all have index 0. So to get something more interesting, but if we have a splitting of the bundle into even and odd parts, then d plus minus may have interesting index. For example, if we take C equal CL dx, then C plus we take C plus lambda even, C minus lambda odd. And we get something interesting. And now let's consider well, after we reconnect, let's consider another more systematic way of finding such a splitting, and we'll also see that this would generalize the signature operator. Okay, I think I saved everything. So let's disconnect and then reconnect.